Are you able to see it?
Yes.
Okay, great. Um, cool. I'm David May. I'm a fourth year computer science student at UCR. And over the last year, I've been working on my honors capstone project, and that's what I'll be presenting about today. My faculty mentor was Dr. Aaron Seitz in the psychology department. Um, and yeah, let's just get started. So what is brain training? Brain training is pretty comparable to physical training as far as the way that you can repeatedly do some sort of exercise to get stronger, to improve your overall strength. You can also work on certain aspects of mental fitness, pretty much by performing particular brain training tasks. One aspect of mental fitness that we can improve is fluid intelligence. And fluid intelligence is pretty much defined as the ability to solve new problems without referring to prior experiences. And that's what my project sort of focused on testing. So how can we measure fluid intelligence? Before we can get into that, we have to kind of understand two concepts, and that is specific and general intelligence. So specific intelligence, an example of that would be like fluid intelligence. Um, and then general intelligence is just basically the amalgamation of all of the types of specific intelligence. And going down that same line, when we do a brain training exercise, what we really want to do is improve that general intelligence. So we don't want this person that's working on this brain training program to just get better at the actual task that they're doing. We want them to overall have tangible benefits in their everyday life. So one idea for how we can measure fluid intelligence might be to track improvements in game performance. So if we have a research study and we have these participants working on a brain training game, and that game is supposed to be tracking fluid intelligence or improving fluid intelligence. One idea would be to just track improvements over time in that particular game. But as it turns out, that's not that effective because it's not actually measuring that general intelligence that we talked about. Instead, it's just telling us, if they're getting better at this very particular task that they're doing over and over. And that kind of brings us to matrix reasoning tasks, which was essentially the focus of this whole project. So matrix tasks have been around for a while. The first one that was really popular was Raven's Advanced Progressive Matrices. And this was essentially, I believe it came out in the late 30s, so it's very old, this concept. But this particular test had some limitations as far as it took about 40 to 60 minutes to complete. So it was pretty time prohibitive. And it also was required to be administered using physical test booklets and answer sheets. So it was sort of cost prohibitive because you had to pay for shipping. And if a researcher wants this, they have to pay a lot to this particular company. And along with those two limitations, it also had a pretty limited problem set. So there just weren't that many test questions that could be administered. The Sandia generated matrix tool tried to answer that last limitation, and it was essentially a tool that could produce a huge number of variants of matrix problems in the APM style randomly. So it would just be like automated. The issue that this had was that if you look on the right here, this is an example of one of the matrix questions that was generated by that Sandia tool. And it just kind of has a lot of overlapping features. It's kind of hard to discern where shapes start and stop and all that. So that was sort of the limitation of the Sandia tool. The UC matrix reasoning task is a more recent test that came out within the past couple of years. It was developed between Aaron Seitz and a couple other professors at UCR and UCI. And this answered a lot of the questions or a lot of the problems that people had with the APM test because it could be administered on tablets without a proctor, so it was a lot cheaper. It could also be completed within 15 minutes as opposed to 40 to 60 that it takes for the APM test. But it still faced some issues. Specifically, it didn't have that many problems. So a similar issue to APM. So we're just going to look at two examples of the type of problems that you'll see on these matrix tests. They can pretty much be broken down into logic problems and object transformation problems. So on the left, we have a logic problem, and this is specifically, it's called an OR type logic problem. So basically the way we can solve this is by looking at the third square in each row and each column. So if we're just looking at this top row, I'm not sure if you're able to see my mouse, but I'll just try to describe what I'm saying. So So in the third square on the top right of the left side, we just look at whatever is in this top left square and this top middle square. And if the shapes are in either of those squares, then they need to be included in the third square. The same thing can be done for the left side. So in the top left, we have a red circle and a blue rectangle. So we have to include those in the third square at the very bottom left. And also we have to include these two yellow circles that are found in the middle left, because anything that's in either the top or the middle will be included in the last. That's pretty much how you can solve a logic problem. As far as object transformation problems, this is the other type that you'll encounter in a matrix test. And these pretty much have any given number of transformations. And transformations can be things like, they're pretty much just the variables, the things that we're changing within the problem that you have to identify to solve it. So in this particular one, the shapes are changing, the shade is changing, and also the rotation is changing. All right. So as far as what my actual project was, it was essentially trying to improve UCMRT by adding a random problem generation feature. So it would be similar to what the Sandia tool did for APM, except for UCMRT. And we would also be a lot more careful about how many problems we produce and the limitations that we put on those problems to make sure that we don't get overlapping features or anything that makes it hard to discern, like we found in the Sandia problems. And the purpose of doing this random generation is essentially to make it so that we have a large backlog of problems that we can use in studies. And the reason we want a large backlog is because it's going back to fluid intelligence again. We want to be able to test people and not have them recognize the problems that they're doing. Right? Because the whole idea with fluid intelligence is that you're not basing your answers off of prior experience. So if we have a large set of problems, we can repeatedly give the same individuals these tests and they'll never see the same problem twice. So they won't have any sort of recognition of the problems. So as far as how far we've gotten currently, we've created a manual problem generation tool. And this differs from what we had before because prior to this project, we basically had to use MS Paint or a similar program and hand draw these shapes and make all these problems by hand. But now with this tool that we've created, we can just define the shapes, specify their positions, and then export in a JSON format, which is essentially a text file. I'll go into a little more detail with these steps. So essentially on the right side of the screen here, you see the page where we define our shapes. So if we clicked edit on one of those, it would come up with a whole list of basically features of the shape. So it could be the size of the shape, the color of the shape, whether or not it has stripes, things like that. So once we define every single shape that we're going to include in our problem, then we specify the positions within that matrix that you saw earlier, and then we'll have a completed problem. And we can export it in the JSON format, and then later on when we're trying to administer the test, we just need to import that JSON format again. So currently we have a pilot study that we're working on. We're pretty much giving, we've recreated all of the original UCMRT problems using this new program, and we're giving that to RAs at UCI so that we can validate whether or not they lost any accuracy when we transferred them from the original problems to this new program. So where are we going to go from here? Because this is, of course, just emerging research. After we validate that our program is producing problems that are as accurate as the original problems, we need to work on specifying all of the rules that our random generation will have to follow in order to avoid those cases we talked about earlier, like overlapping shapes or any instances where it would reduce the accessibility. So for instance, if we have two shades on the same problem that are very similar, then someone with like low vision would have trouble differentiating between them. We need to avoid all of those cases. So that's the first step, specifying all the rules that our program will need to follow. And then it'll just be from there writing the code to just fill in all those fields by itself. All right, that is the end of my presentation. Thank you for listening. Let me know if you have any questions.
Thank you very much, David.